Hey, hey David. Hello everyone.
Hey Alex, how's it going?
Yeah, great. Finally, we have some sunshine in Germany, which wasn't like that for the last weeks. So I'm totally happy. We have good weather here, and in your place?
The sun is shining. We've had cold and rain, but today things are turning around. Spring has started.
Yeah, right. It's the beginning of May, kind of the time for spring to
Yeah,
come eventually. Good.
one would hope.
So, yeah, everyone, that's Alex and David from DataStax Developers. If you can hear us, if you can see us, please set the thumbs up in the YouTube chat. That means when you answer like that, we can start. We have a stockpile of content for today. We are working heavily on very important things to make your application successful and efficient. So looks like it's all good. Cool. So then let's starting. It's a hands-on lab we will be doing today. With me, I am Alex Voloshev, developer advocate lead and head of developer education at DataStax, and my job to help you to succeed with your heavily loaded applications, what use NoSQL databases, distributed by nature, and all the cool things what you need to do in your job. And today with us, David Chung. David, please.
Yeah, my name is David Chung. I'm with DataStax, also in as a developer advocate. My background is development and architecture, and I come to DataStax through the Java world. I have sort of a varied tech background. I've been in the industry just over 30 years, and I've worked in everything from defense systems to machine controls to mobile apps to big enterprise apps, and now databases working with Cassandra. I mentioned I'm a Java person, and I always tell the folks I work with my phone number is 431 Java, and my license plates for one of my cars is in fact Java. So I speak Cassandra and everything else tech with a bit of a Java accent.
I love it. And actually, I have to mention, I really like your Twitter handler, Chunk Fu Coder. Yeah.
That's right, baby.
Hey, I see Aaron Plots with us in the comments section. Thank you for joining, Aaron. Guys, we have like a totally insane skill level crew workshop team here today with like David and me already count around 50 years of experience in software development and IT, but with Aaron it goes over 100 years already, I guess. Well, a bit of joke, but all we are getting close to a century of experience. Good.
That's right.
Cool. So, but actually, as said, there are a big crew behind the story, and yeah, there is a plenty of people from DataStax developers crew who helped us or who designed this workshop. So, uh, let's keep moving. Things we and you need to know about this workshop is what platforms are we using and what platforms we will be using for this run for this workshop. First, our primary streaming platform is YouTube. Mostly probably you are watching us right here. Then we will use Discord, and you can get to our Discord with the help of !Discord command. Um, because you see, you can ask your questions on YouTube comments, but then the workshop is gone, stopped, then we will not be able to answer you anymore. So feel free to join our Discord server. For Menti, we don't do Menti today, but few more things we will need to use and to know. First, everything we do is open source. So everything, all the materials for this workshop, if you want to explore more backend, Java part, Spring part, or if you want to explore more front-end React part, it's on GitHub, and you can get to our GitHub repository, and you will do it actually very soon with the hands-on part with David. Then, as it's like hands-on workshop, so you will pushing the buttons, working with application, launching it and building and so on. We obviously need integrated development environment, IDE. You can do it all locally, but for this exercise, we are using Gitpod. Gitpod is a cloud IDE in a browser, so you don't have to install anything, and you can do it everything in your browser. And then finally, to keep our data persistent, we will use Astra DB. Astra DB is Apache Cassandra as a service. If you never have heard about that, Apache Cassandra is extremely powerful, top-tier, distributed, decentralized database storage. Of course, all these workshop materials and services use it are free, so you don't pay, you don't enter your credit card, and so on and so forth. They are available for training completely for free.
And one more thing on
Yep.
the hands-on,
Yes.
just in case we get moving really fast, and we'll be talking about Java some, so I may get really excited and move really quickly. If we run out of time and you're not able to keep up with the labs as we go, that GitHub page has all the instructions step by step, and of course you'll have the recording of this session, so you can don't feel bad if you're not able to finish the hands-on exercises during the live session. You'll be able to follow through the recording or GitHub or both after we're done.
Yes, very right. You see, we have many dozens of people of very different experience and background. Some of the students of the first courses of the first years, and some might have like extreme level experience already. So if you are a little bit behind, it's totally fine. It can be like that. Materials are open source available, and we support you using our Discord server tomorrow, next
Right.
Monday, and so on and so forth. So don't feel lost. We will support you even then this workshop is over. Thank you, David. That's a very good notice. You are not alone. You are with us, and we are with you. So, we are going to speak about multiple interesting things today. We are going to discuss application design for this e-commerce application. We will cover databases parts for this application because data is extremely important. And we will speak about business functions and things we are going to handle with that. Work with application code, speak about external service integration, and then we'll see you next week. See some more options we offer for you to do next week. And we start with application design. I believe with all the time I working in software development is as developer, team lead, as an architect. I really think what it's a skill. Like there are dedicated architects in each team or in many teams, but I do think what each developer, each decent developer must be thinking like an architect. So we always be thinking about restrictions, design decisions, and first of all, purposes of application. Let's start with application design first. It's the most important thing for us in the beginning. I hope most of you have a basic understanding of three layers of architecture of a normal application. Every application usually will be storing some data. Will have some data tier. It will have some backend layer, and it will have some presentation tier or front end. And obviously, there will be some clients working with this application. So here we speak about all those components. It's a little bit extended application because most modern applications, they're not strictly limited to those three. There's going to be some external services for authentication, for example. So going from the left to the right, we will be speaking about the following elements: clients, presentation tier or front end, service layer backend or backend, and data tier or data tier. Yep. For us, clients going to be mostly browsers and progressive applications. Doesn't matter currently, and it doesn't matter so much if it's going to be mobile browsers or web browsers. Before, it could have been a big deal, but this dark era is over. That is very good. So on the presentation tier, we will have a front-end application On the backend, we will have backend application, and on the data tier, some database, and backend works with some external services. First thing, we need to define what technologies we are going to use for the presentation tier, what runs in a browser. It's easy to pick language because so far, as I know, the only real option is still only JavaScript or TypeScript transpiled into JavaScript. But then we go with some more advanced things. This application we will be launching and playing with today is written using React and Tailwind CSS for visualization part, and it's based obviously on JavaScript, pretty obvious. So for our Astra Commerce application, we need to define which technologies we are going to use, which APIs we are going to use. And story here is very simple. For front-end part, we are going with React. And for backend part, for the API of communicating, for the front-end communicating the backend, we will go with plain old school HTTP protocol. There is still a very solid solution for our REST calls. And for backend component working with a database tier, we will use native drivers. External services are to be communicated with HTTP. So, part of the front end, that's actually quite heavy. That's so-called holy war, which front-end framework to use. Like there are so many complications, so many conversations, what should be used. Like maybe we go with Angular, maybe we go with React. There are some other options like Vue.js, for example. We decided to go with React because it's one of the most widely used libraries in this field and very common choice. But there is nothing wrong with Angular or Vue. We just cannot use all three systems for one single workshop, right? For database, choice is much more interesting and much more advanced. Because like although each piece of each front-end application is a single page application, it will be executed in a browser of your customer. So we already easily distributing the workloads because the hardware of the customer will be processing those. When we speak about the backend and then we speak about the database, all of those requests, all of their SQLs will be processed by our hardware, by our company, and we need to make a very reasonable choice of picking the database. For this one, for today, we go with Astra DB, which is Apache Cassandra as a service, and that is a NoSQL distributed decentralized database. Why we go with NoSQL? Because we have, as a successful e-commerce company, let's imagine we all work in the same successful e-commerce company. We have customers all around the world, and we want our application to be fast for them. So we need to have a distributed system with database data centers in each continent. Your application can be lightning fast, but if your American customers work with a database server located in, I don't know, in Europe or in India, for example, it's going to be half of a planet to travel and is still limited by light speed. So it's not going to be fast. Even though your database is fast, your application is fast, but we need to have it to be deployed close to the customers to keep the application running very fast. So we need distributed system which is ready to handle petabytes of data. Like imagine how many Amazon stores data, like we speak about petabytes and petabytes and petabytes of information. And also we need to have something dispatching those very quickly. So we go with NoSQL database because there are basically no SQL database what could handle those requirements. And as architects, we need to think about requirements all the time. Why we
And
go? Yep,
Alex,
yeah, sure, shoot.
the other thing about this diagram and the choices here, the other thing Astra DB gives us is super high availability.
Yeah,
That
right.
the distributed nature of that is going to make it highly available. Even when you look at this architecture, back where Alex talked about the front end and choices and choosing React over Angular, for example, the fact that we have done a good job of defining this architecture in layers and exposing the API from that back end layer to the front end using HTTP REST means that we can sort of be agnostic about the front end. We could build an Angular front end and a React front end. Not that you ever would, but you could interchange them very nicely. So Alex is right in focusing on the architecture. It's more than just code, it's how it fits together and making good decisions along the way.
Yeah, thanks, David. That's totally right. So Apache Cassandra provides all the requirements we have for data, um, fulfills the requirements we have, but also we don't want to be maintaining it. So we want to use a managed solution. That's why we go with Astra DB, which is basically managed Cassandra as a service, geographically aware, distributed everywhere, and scalable, but we don't have to do all the operations on it manually. They will be done by our provider. Let me switch back. Good. So for the backend, for data tier, we go with Cassandra, or Cassandra as a service, so Astra. For the front end, we go with React and JavaScript and Tailwind. For the backend components, it's going to be Java. Like if you see David in the workshop, mostly probably it's going to be Java. And Spring Boot and Spring Data with some external services with Google. Okay. Um, so, very important thing for us, we start from right to left. So first we want to establish foundation, the place where we will store data. Data actually for modern applications, for modern businesses is most important thing because like, could you imagine what would happen if Facebook would lost all of their data? The company would be just destroyed. Doesn't matter if they have all the hardware, all the networks, everything, even all the employees with no data of the customers for all those dozens of years, it would cost nothing or very, very close to that. But if they would just like eventually lost a couple of data centers, they can recover pretty quickly. We have to put proper attention to the data we are working with. It's the most important thing. So that's why we start right to left, going from data tier. And for that, first thing we need to understand for our e-commerce application is the foundations of the database and why we are picking this one and not another. So Apache Cassandra is a distributed, decentralized NoSQL database. It's a very powerful, even single Cassandra node is very powerful and very fast. But what really matters for us is so-called masterless or peer-to-peer architecture. Traditional databases, most of you have experience with, like traditional relational databases, they are designed in work in so-called leader-follower architecture. Like we personally, we use it to call those master-slave architecture. Now we are switching to leader-follower terminology, but the idea is basically the same. There is a primary server you can write and read, and follower servers you can read only. I hope most of you have experience with whatever Postgres or MySQL or Oracle or whatever. Cassandra follows totally different architecture. Cassandra is a peer-to-peer database, so each server can answer every request, is it write or read, and each server communicates with each server, not just followers following leaders. Apache Cassandra first was designed by Facebook employees to solve problems of the proper size. It's ready to work with data of any size, and we speak about petabytes and petabytes. It has extreme level of read-write performance, scales linearly, so there is no overhead of adding more and more nodes into that. It has highest possible availability. Like if you need to have really 100% uptime, and big companies definitely do want to have it, then like Apache Cassandra will be one of the obvious choices because of this peer-to-peer nature availability. An outage of a single node doesn't lead to an outage of a whole cluster. Actually, even outage of a data center doesn't lead to an outage of a cluster. In case you have multiple data centers, of course. It's very well prepared for automation. So very many operations are totally automated and executed by the cluster by itself, including self-healing capabilities after recovering after outage automatically. Not always possible, but for many of failure scenarios, it will apply self-healing pretty well. Geographic distribution, so being deployed in multiple regions, platform agnostic and vendor independent. Platform agnostic means you can run it on every cloud, on your own data centers, on premises with ease, and well, with some adventures. That's why we speak about, that's why we will be using Astra DB today, not exactly Cassandra, because we want to outsource this headache of maintaining this and still being in non-vendor lock-in situation. And that's also vendor independent because it's managed by Apache Software Foundation, not by some commercial companies, open source
And
community. Yep, David.
Alex, let me jump in on
Of
Astra as
course.
well. The other thing about Astra, I like to think of Astra as what Cassandra would have been if it had been designed today in a cloud native world. Cassandra is just over a decade old, and Astra really takes those great ideas from Cassandra, puts them into a modern cloud native context. And one of the important ones that Alex touched on is Astra is, some people say zero ops. I wouldn't say that. It's very low ops. So very little work done to keep Astra up and running. In fact, scalability in open source Cassandra, it's a big effort to scale up a cluster and bring nodes on. It's certainly doable, powerful, scales linearly, but you have to manage that and really shepherd that process. In Astra, we call Astra serverless. Obviously, there are servers running behind the scene, but you don't have to deal with them, which is awesome, which is really awesome about Astra. Really takes
Right.
Cassandra into a modern cloud native environment.
Hmm. Good. So um, now there is a very important things to understand. Cassandra is different. It was designed to answer problems what traditional relational database could not answer at all, especially for the scalability. First thing we need to understand is data is replicated. So each piece of data will be stored on multiple servers, very often on multiple data centers. So it will be available in all your data centers in United States, in Europe, in Asia, in Australia, and so on and so forth. But even more advanced thing, even more important thing is what data is distributed. If we have like a table like that with data of a population per city per country, how it could be stored on Cassandra, for example. In traditional databases, you have a copy, you have this table in full of your master server on your leader server, and you have it also in full on each follower server. And if it's too big, if the table is too big, you run into problems. You have to upgrade your servers, which requires downtime. And then if it doesn't fit anymore, you have to do sharding. And sharding on relational databases is a very painful problem. Cassandra was designed to solve this natively, smoothly, with zero downtime and completely automated day. That means what actually table will be divided into pieces, and those pieces will be distributed across multiple servers. It gives us very powerful thing because each server is responsible for part of the table. If your table gets bigger and bigger, if you get more and more data, then you just can easily add more servers into this cluster, or Astra will do it for you because it's serverless. Um, and then you just have your data, move it in smaller chunks into these new servers. So each server has again less data and can dispatch higher count of queries per second. Node is, nodes. So node in Cassandra terminology is just a server with Cassandra running on it. Good. So the data structure for these will be very familiar to you. It all starts with a cell, which is an intersection of a row and a column. And row is a single piece of a single item in a table you can access. But really important thing, and the most important thing what people with experience of relational database are not used to is the partition. The story is each those partitions, they are very important. They're always stored together because they share same partition key. For example, for this table, we made partitioning based on the country. And that means what cities of the same country will be stored together as we see, for example, all cities of Canada will be stored together, or cities of the United States will be stored together, and so on and so forth. This keeps our database scalable. If you run small to medium business, you really may not need it so much. But for big projects like Netflix, projects like Amazon or Apple, that as a real pain because they handle so much data what single relational database cannot handle. Good. So, good. And then finally, table is a group of columns and rows storing partitions. Biggest these so people take a look. Even working with Astra still will require a lot of understanding, and sometimes let's say some pain to handle, because when you work with distributed data, we have to admit it's harder than working with one server storing all your tables and all your data. But in the modern days, modern projects where developers get like the best salaries, they are tremendously huge. That's why we go with Cassandra, what can answer those. Um, Apple scale, if you have Apple, if you have iPhone, if you have MacBook or anything like that, you're already a Cassandra user because Apple is one of the biggest Cassandra users. And developers, by the way, because they also contribute to the development of Apache Cassandra. Uh, they currently, this the slide of a couple of years, we were running more than 160,000 Apache Cassandra servers, but by this time they are actually running 300,000 Cassandra servers, storing hundreds petabytes there, and dispatching several dozens millions of operations per second by now. But my favorite use case is actually not Apple, although they are biggest or one of the biggest, but Netflix. Problem with Apple, what they don't say a lot, or how exactly they use Cassandra. Netflix guys, are there any Netflix users in this chat that would be interesting? I'm definitely an active subscriber. So Cassandra is the #1 database for Netflix. They use it all the time for most of their projects, and they also contribute and develop many things to make Cassandra better. You see, like as there's some competition in between of businesses like Apple TV or Netflix, there is a strong competition. But despite that, we're working together. That's what open source technologies do, and I really love this part. So, a couple of years ago, Netflix reported what their single most active Cassandra cluster handles 30 million operations per second. That's the single most active, but actually they have hundreds of clusters. Maybe not of them have this kind of a workload. Good. But overall count of operations per second, we speak about hundreds, millions of operations. And many petabytes of data. That's for sure. Good. So why they are using this? Cassandra's trademark is multi-data center deployments. So single cluster consists of multiple data centers, and each data center consists of multiple servers. It's very important for the customers because we keep data close to customers. It's very important for disaster tolerance. So even if you have a real disaster, typhoon or whatever, tornado destroying your data center, your other data centers with this data will be available. And finally, all data centers are active. What that means, it's not like for most of the relational databases, or actually not only relational databases, but for many NoSQL databases like this as well. All data centers are active. It means what in each and every data center you can write and read data. For most of the databases, it wouldn't be like that. It would be active-passive distribution. So one data center is active, you can write and you can read there, and all the others are passive. So you can read only if you do a write operation, although from Australia or United States, you still will have to do it in your active data center, which might be, I don't know, in Sweden, for example. Why not? So that's the story. Okay, Cassandra, all data centers are active, and that is a killer feature, reading. So I mentioned already, Cassandra is not bound to any platform or service provider. Even running it with Astra DB, you can choose Google Cloud or AWS or Microsoft Azure. You will see it very soon with David. Um, but you can also run it on premises with open source Apache Cassandra. And it's vendor independent and it's controlled by Apache Software Foundation. If you know Hadoop or Spark or Kafka or Maven, if you do Java, you know Maven, that's for sure. It's all Apache Software Foundation projects, as many dozens, actually hundreds of others. So, with Cassandra explained it, and we partially already explained it by Astra DB, because it's the same but with no operations. So we will care about application, about customers, not about running repairs or backups for the database. That's what matters for us. Why not relational database? I've mentioned a couple of times. Relational databases are great. Some people say what NoSQL will replace SQL databases. That's a complete bullshit. Relational databases are great. They are here to stay, and we love them. And for many projects, they will be better choice. Problem with them, as soon as volume of data grows more and more and more and more, they can't cope with that anymore, and you go with sharding, and everything is slow. You can do joins and query data from multiple tables with relational database. And that is pretty cool, but there is a problem. It all works very well as soon as the information you need to join feeds into a memory of a single server. As soon as you are going to join over huge tables, it will not work at all, or it will work extremely slowly. And you know what happens with your customers when you are very slow, when your application is slow? They go to your competitor. For our e-commerce application, we cannot afford it. So the point is here, understand the difference between OLTP and OLAP. Traditionally, relational databases were in between, playing a little bit on OLTP side of the field and on OLAP side of the thing simultaneously because they are versatile. Versatility is a really cool thing. Like it's a really cool thing, then you can afford it. But you know what? Before in humanity, each like thousands of years before, each person was a gatherer, hunter, farmer, I don't know, doctor, if that's applicable. Um, he was doing everything, but over time, humanity developed specializations. Now we have programmers, now we have real doctors, not shamans. Now we have teachers, now we have drivers, and so on and so forth. Why did we do that? Because specialization is efficient, because like it helps us to do our job better when you don't have to grow food and then work as a programmer simultaneously. You can do it as a hobby, but not as a primary job, right? So, why I'm talking about that? Because exactly the same thing happened with the databases. Databases were versatile and like multi-purpose in the beginning, but now more and more databases are specialized on OLTP side or OLAP side or on some specific use case, actually, like time series databases. OLTP means we need our data fast. Usually it's customer facing data. So it's data what your client's working with. It has higher number of transactions, and these transactions have to be executed within some very, very few milliseconds, or your customers go to your competitor, and everyone is disappointed. On the other side of the field, there is online analytical processing. Online analytical processing is a job done by analytics in our e-commerce platform. So it usually like they want to explore all data, understand customer behavior changes over months and months and months. That's often about high volumes of data. That's often works with cold data, what's not accessed so fast. But most of all, we can afford being slow here. Like when we are doing some kind of analysis, we can run select queries over our data, what will include dozens and dozens and dozens of joins. Once in my life, I've seen an exception, actually two times in my life, and I've seen an exception. You cannot have more than 61 join in a select statement. It was like some 6, 7 years ago on MySQL, I believe. Can you imagine maintaining a query with 61 join in it? It was quite painful. Yeah, so when we speak
Sounds like a
about data,
nightmare.
oh man, it was. Yes, yes, it totally was.
Wow.
And like worst, you see, for me it's hard to maintain, but I'm at least I'm getting paid for it, right? So it kind of makes sense, but our customers are paying to us, and then they have to wait for a minute to get the data we want to see. That's unacceptable. So OLTP kind of workloads is for customer-facing data very, 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 very fast. And OLAP is for our analysis, for our marketing purposes, and we can afford waiting for those because our employees are getting their salary. So if query works slow, we will just go get some coffee, some water, and chat in a cafe, whatever, waiting for the data to be processed properly. So Apache Cassandra is OLTP specific database. It works extremely fast, having billions of rows and petabytes of data across all the continents customer facing. But there is always price to pay. When you are in the middle, like traditional relational database, you are kind of OLTP, but not so fast under a real load. You are kind of interlap, but not so much. And if you want to go to one side, then you pay for that. I mean, not by the money, but the capabilities. So Cassandra is OLTP specific. It means what for search and analysis purposes, you might need also to put your data in another platform, like we do using uh, Apache Pulsar, for example, to stream data from Cassandra to Elasticsearch or to, for example, I don't know, whatever Apache Spark solution, right? So we can make analysis or machine learning over this data. Good. Very often people ask us, why don't we use a document store like Mongo, for example? So people, don't get me wrong, Mongo is a great database. I love Mongo. I worked with Mongo a lot. Mongo is a great database, totally. But it's designed for different use case. It still follows this little, more or less follows this little follower architecture. So it's not so scalable for writes, that's for sure, much less scalable than Cassandra. It works good for smaller size of a project. People say it's schemaless, which is kind of cool, until it's not, because if you have a lot of data, which has to be accessed very, very quickly, OLTP, you remember? And schema gets important. Last year, I was at Mongo local conference in Frankfurt, and of course, I attended a Mongo-specific data modeling workshop because data modeling for NoSQL databases are extremely important. And you know what? That's was data modeling for Mongo is actually also very important, although it's kind of schemaless, but not schema flexible, let's say. And then you have a lot of data. Schema gets very important, and you need to really think about that. So there are so many similarities from data modeling point of view. So story is we want to be available on each continent, and we want to handle petabytes and return customers' queries within milliseconds. And well, high availability is better with Cassandra, I would say. With Astra, we discussed already. No operational overhead, geographic awareness, no cloud vendor, so you can move to another cloud provider if you would like to. And that will be it for now. That brings us to our first hands-on. We are starting to build a data tier for our application. So, David, I
Let me share my
guess,
screen.
yes, please. And I'm ready to switch us to your screen any moment as soon as you're ready.
I'm ready.
Yep. Boom, boom. You are live.
All right, sounds good. Well, we're going to take a look at the hands-on portion or part of the hands-on portion of this material. And where we're going to start is on the GitHub page. And I shared the link in the chat. This is the GitHub page, and this has access to all the materials we're going through, including the slides. There'll be a link to a recorded version. There's actually a link to an older recorded version of this workshop. And being GitHub, in addition, you see here, we have the source code that we're going to be working with to put all of this together. So GitHub is going to be where we do the work. The first thing we're going to do in this first hands-on exercise is create an Astra database. And to do that, you'll need to create an account in Astra. As Alex said, Astra does not require you to give DataStax your credit card. In fact, you get $25 a month worth of free usage, and that's actually a large amount. DataStax doesn't even have my credit card. So, it's not one of those where you have to opt out later or you might forget to pay. So we'll create an Astra account. Also, Alex mentioned something about streaming in Pulsar. In addition to Astra DB, at DataStax, our Astra product includes a hosted Pulsar or streaming service. So we're going to actually use a little bit of both. In this e-commerce application, there are some things that need to respond to the consumer right away. I've been doing a home remodel project, and I've had to do a lot of online purchases with the home improvement store. So I go and I place an order and fill it out, and I'm going to go pick it up for lumber and stuff like that. But my interaction online with the store has to be fast. I want to order this door or this cabinet. It says, yes, we've got it in stock. I put it in my cart. I give them my payment info. I get an email confirmation right away. But in order for me to go and actually get that cabinet or door, I have to go drive to the home improvement store, and someone in the store has to go and find the cabinet in their warehouse and take it back to their pickup area and mark it as being pulled and ready to be picked up. That's a part of the commerce process, and that part is done asynchronously. I don't have to wait at my browser for someone to drive a forklift and pull a cabinet off the third layer. So that asynchronous behavior, we're going to create a couple of Pulsar topics to send persistent asynchronous messages to handle that sort of stuff, pulling the order and all of that. We're just going to simulate that, but that gives us a good simulation of a real e-commerce application and also exercises some parts of Astra beyond the database. So Astra DB is the database, Astra Streaming is our hosted Pulsar service. So what we're going to do, this is the GitHub page, and step 2 is create your database. So you're going to go to astra.datastax.com, and you can create an account and sign in. You can use GitHub or Google, or you can create an account with your email address. I already have an account, so I'm going to sign in with a Google account. And thank you. I have to sign in through my I will sign into this account instead because I have the credentials already in there. All right, and this is the Astra interface. Just a note, the interface has been updated since this GitHub page was made. It's a much cleaner, simpler, in my opinion, more useful interface, but it won't exactly match what you see in GitHub. So if you're doing this on your own, I would take a look at the video as well as the GitHub. But what we're going to do, it says step 2B, create a database on the free plan. So over here on the left, I'm going to click on the databases. And I probably have a database already called Sandbox DB, but I'm going to create a database. I'm going to click on create database and give it a name. The database name is demos, and the key space name is e-commerce. I don't think we've talked about a key space, but a key space is roughly equivalent to a schema in a relational database. And the key space serves as a namespace or a demarcation in which we put tables and a few other things like user-defined types. So e-commerce is the name of my key space. And then you can select a provider. We support Google, Amazon, and Azure clouds, but we don't have free access in all of them. So I'm going to choose the Google Cloud, and then I have to choose a region. And you'll notice there's a bunch of different regions here. Let's see, are all these unlocked? Looks like they are. I'm going to choose, since I'm based in Iowa in the US, I'm going to choose US West Central. So there, I've chosen a database name, a key space name within the database, a provider, GCP, and a region, US West Central. And you'll notice the costs are actually based on the provider and region. It gives you approximate costs. So I'm going to say create the database. And you'll notice the status of the database is pending. So we're going to wait a minute until it gets out of the pending state, until it turns to active. Here for the database, you'll see there are different tabs. There's an overview that gives you information about the database. There's health, and again, you're not seeing anything because the database is pending, but this is where you would look at health. Here, the Connect tab gives you ways to connect. You can choose APIs and useful code information that you can use to start working with your database. CDC is our change data capture, and then settings for the database. And we're going to come back to and do most of our work in the CQL console. The CQL console is going to give us a shell in which we can enter commands to access the database directly. Of course, you could run our Astra client or Astra CLI locally on your machine and issue commands remotely to Astra. So it'll take just a minute or two for this Astra database to come up. But once it does, so we're waiting for step 2C to complete, we're going to then go in and create, in fact, we can do this now while we're waiting, we can create the streaming pieces. So this icon looks like wind blowing. It stands for streaming. I'm going to click on that, and we're going to create a tenant. So I'll create a tenant, and we have to give it a name. Very important, the tenant name has to be globally unique. So I'm going to call mine e-commerce, and I'll use my initials. And I could probably spell e-commerce correctly. E-commerce D-Chung. And then I'm once again going to select a region and choose US Central. And again, you see some information about the costs for read, write, functions, storage, and so on. We'll create the tenant. Inside the tenant, we're going to create topics. Topics are similar to JMS topics, or if you're, depending on what sort of streaming or messaging framework you're used to, but the system will use topics to send and receive messages. And these messages in an e-commerce system might be, like I described at the home improvement store, a message to tell a forklift operator to pull down a cabinet from the fourth shelf in building C or something. So I'm going to open this up, and namespace and topics. I'm going to take the default namespace and I'm going to create some topics. And you see I'm scrolling on the left here in the GitHub repo, and there are 4 topics we're going to create. Pending orders, picked orders. A picked order is one that's been pulled off the shelf, shipped orders, and then completed orders. Or in the case of my home improvement store, that would be picked up orders, when the customer has actually driven their pickup truck to the store and retrieve the items. So I'm going to add a topic, pending orders, picked orders, shipped orders, and completed orders. Notice that these topics are persistent. And what that means is that it's the responsibility of the topic, once it's received a message, to make sure that message persists, even if a server in which the topic is running fails. And for an e-commerce system, orders are our lifeblood. So you can't lose an order. So that's why we've chosen persistent for topics. The focus here isn't really Pulsar and how topics work, but just wanted to note that's why we want to make sure that we've chosen persistent topics. Okay, I'm going to go back to the database and just check. And it looks like the demos database is active. There's the status, active. So let's continue to look. That was our step 1. Step 1 is to create the database and to set up the topics to use streaming or Pulsar. So that's where we'll leave the hands-on stuff. Again, if you had trouble keeping up with that, you have the video, or you will have the video to follow, and all of the information that you need is in the GitHub repository. As I mentioned, the GitHub repository has the previous version of the Astra UI, but I think you'll find the new version, it's similar enough you can follow, and the new version is actually cleaner and simpler to use, in my opinion. All right, so Alex, I think we're going to get ready to turn things back over to you to start talking about the data modeling and schema, and then we'll return and build the schema in Astra. All right, back to you, Alex.
Yep, give me a moment.
Okay.
Yes. Okay, people, so let's move on. Now, with a database already available for our application, normally it would take quite some hours to set up the things, even if you have servers running, right? But it went very smooth and quick with the managed approach. We will talk about now how do we design our data model? How do we create proper tables for our data? Funny enough, many people think what NoSQL is always schemaless. That's a complete bullshit. There are plenty of databases, NoSQL databases, that require strict schema, and that's perfectly fine. Those just for different use cases. So we need to understand how do we store our data, because if we do it wrong, our database will not be efficient, our application therefore will be slow, our customers will be unhappy. What happens with when customers are unhappy, you perfectly know without me. So, and to design our data model for our application, properly, because performance is a shared responsibility. Cassandra does its job, but you have to do yours. Then we need to understand what exactly we are going to do with the data first. Again, it all comes from the requirements. Think like architect. For our case, we speak about following e-commerce system functions. We will speak about product catalog, shopping cart, user profile, and if we will have enough time, about order processing. So, story very simple. Everyone understands what the online store is. You can order something. To order something, you need to see product catalog and choose some goods. You put them into the shopping carts, then you do some payments, and then you have your order processed. Must be pretty obvious for all our attendees. Now, I hope most of you have experience with relational databases, right? So things like normalization, things like normal forms and foreign keys and joins must be familiar to you, I hope. Take a look. Working with data in a relational way, we traditionally start thinking about the data and analyzing raw data. We identify entities, domain entities we are going to work with. We identify their properties, relations between them. When we design tables using normalizations and foreign keys, and then we have to query data from multiple different tables simultaneously. We will use joins, joining data from different tables, normalized tables. That, I hope, sounds very familiar to you, so you understand what I'm talking about. And normalization is good until it doesn't. What does that mean? It means that there are plenty of scenarios then actually your use case is not so good for normalized data. But first, let's speak about benefits of a normalization. Normalization has very efficient storage use, so you don't have any duplication. Each piece of data stored only once, right? So you kind of save money on your disk space, which sounds good. Also, normalized databases with relations, they are better in maintaining data integrity. So you can have things like on delete cascade or foreign constraint checks, all things like that. So great things, right? And like best benefit of normalized data is simple write. If you're going to transfer an employee from one department to one other department on this example on the right side, you're going to run one update. If you're going to rename a department, you see here, it's going to be one update. If you're going to add an employee and assign it to some department, it's going to be one insert, simple and quick. So normalized data is good for efficient storage use, data integrity, and simple writes. But nothing comes with no costs. There are always some price to pay. What's the trick with normalized data? Slow reads. Then you have to read, then you have to show profile for your engineer named Edgar Cott, and you need to show also not only name but department he works. Then you will have to do select something from employees, join on departments. So you will be able to show Edgar Cott works in engineering department, not in department ID number one, because this number one will be useless for your colleagues working with this data. All right, people need some meaningful names. And it works very well as long as the data you work with is on a single server, or at least it's on multiple servers, but the join you do fits into the memory of a single server. Then it can work efficiently. But still, more joins you have in a query, slower it gets. And then obviously complex query model. I told you I was maintaining queries like 60 joins in a single query. That is a real nightmare, like real nightmare. David is perfectly right. So that's the story. Now, normalization approach when one table serves many different queries does not work for huge distributed data systems. Normalization will not work for Netflix. Normalization will not work for Apple or Facebook people. Very simple. We need at some point to normalize, denormalize, sorry. So modeling your data, designing tables for your NoSQL data, um, tables or collections, doesn't matter. You still need to think about proper denormalization. It goes exactly opposite way. We don't start with data. Okay, we do work with data still, of course, but really important thing we must understand is how we are going to use this data, or better to say, how our customers are going to use this data. So we must analyze customer behavior first. What is the sequence of, like, what's the workflow? What are the dependencies of workflow? Um, how it going to work? Let me say a word about workflow dependencies. Like usually when developers speak about dependencies, we are going to speak about libraries, right? These kind of things, something you do npm install or Maven build or whatever Gradle thing pulling your dependencies for you. But workflows, the way how people are using your application, they also have dependencies. For example, if we want to show to our customer status of his order, we are going to know the order ID. In To know order ID, we need customer to pick one of the orders he made. So we need to show a list of the orders. And to show a list of the order of a customer, we need to know which particular customer requires to see his order. So he or she needs to sign in first. That looks like a workflow with dependency. Login, so enter login and password. Click on the button Show Order List, click on particular order, and then you can see order details and status. That is a workflow, and those are dependencies of this workflow. You cannot show order details if you don't know order ID, or there is no signed in user at all, obviously. That's workflow and its dependency. Then going with this NoSQL data modeling, we define queries. So we literally write queries, select something from something before we have tables designed. Opposite way, not like in traditional relational database. And then knowing the queries we are going to execute to fulfill requirements of those workflows, we can design tables using denormalization, so data duplication. Uh, Denormalization is a very powerful technology. It's designed for performance to avoid joins. It's designed to dispatch your data very, very quickly. Benefits of the denormalization, very fast reads. You don't have to do one join or two joins or a dozen of joins. You just return data you need to return. And simple query model. Well, anyway, there are no joins in Cassandra because it's non-relational database. Uh, but there are obviously some, it always comes with some costs. What are the costs of the denormalization? First, data duplication. So you will need, on this example, you have now employees table having department ID, a department name in it, but departments table still there, but now we have engineering being mentioned multiple times. So that means what we are consuming more disk space. And you can tell me, we are going to pay for it. Yes, but you know what? Disk space is cheap, and what is really expensive is your performance. Like if you are answering your client query slow, your customers will be disappointed. They will go to your competitor, and you are unhappy. So, okay, disk space costs money, but your reputation and your performance is much more important. Disk space is cheap. Reputation is priceless. Then, manual integrity enforcement. There are no foreign key checks. There are no on delete cascade, things like that. So you will have to do it on the application level. Using NoSQL decentralized database like Apache Cassandra means more work for you as a developer. That sounds bad until you understand what Cassandra-ready developers get better paycheck. So I'm fine with that. I can do it as long as I'm getting better money for it. Yeah, that's survivable. Good. Now, really important thing to understand between normalization and denormalization. It's way easier to run denormalization, so multiple writes. You need to write into multiple tables when you update something. you can run multiple writes in parallel, especially with Cassandra, which can handle millions of writes per query per second. It's very easy. But then you have chain of joins in your read query. Can they be executed in parallel? Very often no, because result of each next join will depend on the result of a previous join, of a previous join, of a
Right.
previous join. You have three joins as a chain with some filtering, with some searching on that. You will have to wait for first join to be executed, then second, then third. It cannot be executed in parallel very, very often. And with writes, no, we can write them simultaneously. So that's why denormalization for performance is significantly better. It comes with problems to solve, right? But if you need like to be very fast, you have no other option. Denormalization very often goes to one table serves one query, and that means you're going to have many tables, and that might be painful, but pain is inevitable. Suffering is a choice. So again, as long as we are getting better paycheck, I as a developer can totally survive that.
And Alex, let me jump
Yeah,
in. I'm in
yeah.
favor of better paychecks too, but I will point out that part of the denormalization, and one of the things that struck me when I first started working with Cassandra, is in order to do the data modeling properly,
Hmm.
I found myself creating multiple tables that had exactly the same data in them, but were organized differently in order to support high performance, different queries at a high level of performance on exactly the same data. That
Hmm.
took a mental change to get used to.
Yes, yes, that's right. It's it has its very, very strong benefits. You
Yep.
see, for me, transition from relational databases to non-relational was pretty hard because, like, when you use
Right.
it to that, like, it feels natural. And these, like, denormalization is evil. I've been told so many times what denormalization and evil, but actually, when you start to get used to that, you realize what we are already doing denormalization for our big e-commerce application I was working with like 6 years ago. We applied denormalization because we needed our customers to be happy, and you have to be fast if you if we want to keep them happy. So yeah, okay, good. Now, uh, but how exactly you develop data model, like now very step-by-step process? That's called a data modeling methodology for Apache Cassandra. And it was designed by our dear friend Artem Tibachko. And we are very proud to share his experience and his methodology with you. Uh, First two steps we need to do before we can proceed is we need to understand conceptual data model and application workflow model. Application workflow model, I briefly explained it to you. We have to identify access patterns, how people are using our data. We describe that with application workflow diagram. Oh, right, yeah, thank you, Doctor, like Captain John Sparrow, right? Dr. Artem Chubatko, right? Um, and second thing we need to understand is conceptual data model. So we still need to understand our data, its properties and relations in between. We describe that with entity relationship diagram. When we have those, workflow model and data model, we map them together and we can have already a logical data model, describe it in Chebotka diagram, using this query first approach I mentioned before. Then we optimize those to have physical data model designed properly. It sounds now not clear at all. People, I understand you. It now sounds like I'm not sure what he is talking about. I'm with you, like I experienced that so many years ago. I still remember with pain. Don't worry. It feels much better when we go smooth, like by use case, speaking of particular example, each one you will understand. Like you, I hope at least once in your life have seen some product catalogs, right? So let's start with that, or maybe more than one time, kind of. So that's called entity relationship diagram, and I hope you've seen it at least one in your life. What do we have here? It's a very simple one. We have some customers, we have some products, and we have some categories because it's a product catalog. User navigates with product categories, and each product category can contain some products, and each product belongs to one product category. Each product has ID, name, description, and price, and each product category has ID, name, and parent. So there can be multiple, like a tree of the categories. So far, so good. Then we need to understand access patterns. So how exactly this data will be accessed. And we know what we need to be able to query product by its identifier. We need to be able to query a product on line price because price may change over time. We need to be able to query product category in a hierarchy. That's our queries we are going to do. So we explored our entities, we explored our data and identified its entity relationship diagram. So we understand what the properties and relations of our data. And we identified access patterns. So how we are going to use that. Query product by its ID, query product, see query product online price, query product category as tree of categories. So basically, mapping those together, we are getting so-called logical data model. We are thinking of the items we are going to have, or like units we are going to have, entities, better to say. We are going to query products by their IDs. So we start thinking about product by ID with brand, description, model, and so other properties we might need. One product might have prices, more than one actually, but for now we describe it like that. Because prices are more advanced, we might need different prices in different stores. So it's a little bit harder than that. When we are going to have categories by ID and categories by parent ID, we will need to get those into the tree of the categories. Those will have linked products. And physical data model, and then we map it all together, leads us to a very simple situation. We will need to have products by ID. We will need to have categories by parent ID with products embedded into that. And we have prices as a separate unit because price may vary on the time or price may vary on a particular location. For example, prices might be different in different regions, a very common situation in e-commerce. Good. And obviously, one product belongs to one and only one category for the simplification purposes here, let's say. And one product may have multiple prices here. Now, one notice on that before we proceed. That's the 2 hours workshop. I'm afraid it will be a little bit longer, but for good, so we can get deeper into some details. What I want you to understand, data modeling is the most important part of working with distributed databases. Doesn't matter if you speak about Cassandra or similar projects, proprietary projects, for example, like Google Bigtable is a great database which is based on the similar principles, but so data modeling idea will be exactly the same with Bigtable. But with Bigtable, why we go with Astra, why we go with Cassandra? Bigtable is a good database, but if you are not happy with Google Cloud and you would like to move to Amazon Web Services, or you would like to move to your own data center and like drop a GCP, you will have to rewrite half of your application. And if it's a big application, it will be hundreds, maybe even thousands of human years. I mean, like working of a huge department to make it happen. With Cassandra and through Astra, you can easily migrate from one vendor to another. Well, easily not the right word, but way, way more easier than you could do with any other approach. And with Astra, it's going to be like one button click at some point. So, okay. But yeah, data modeling is the most important part. You cannot learn it within half an hour. We have a free resource called Data Stacks Academy, where we have a real course on data modeling for Apache Cassandra, similar to Mongo as mentioned before, similar to Bigtable, for example. And you can do it completely for free. I will say more about that in the end. But what matters for real is learn data modeling if you are going to do it and take our free course. It's actually really great. It's designed and developed by people like Artem Chabatko, PhD, who really know these things, really know how to do it better way. Okay, so let's keep moving. When we, with this physical model designed, yep, Spanner is not exactly the same. So Bigtable is different to Spanner. They have both. Spanner is relational. Spanner uses some ideas of a Bigtable, but not the same, definitely. So they both good for different purposes. Yeah. Okay. So price. Price is going to be separate from the product because we might have different prices based on the location. Product is separate from the price. Product is going to have many properties, specifications, linked documents, and images. But notice important thing, with Apache Cassandra and with Astra, we can have, for example, thing like map, text. So this map is going to store different specifications, and it's also very flexible. So it's not exactly just the document, but it's very similar to this idea of the document-oriented databases, because you can have some different specification sets. Because, like, for example, if within Amazon you can buy, I don't know, headphones and I don't know, some furniture, and obviously they're going to have different specifications and different properties. Perfectly fine, Cassandra can handle that. Good. Category. Categories are designed to be called recursively. So they're going to have parents and they're going to have their own IDs. With a second use case, we are going to work on this shopping cart. Idea of a shopping cart of this entity relationship diagram, user can have multiple shopping carts. Shopping cart may have multiple products. And that is perfectly fine to us. Product has ID, name, description, price as discussed, and shopping cart has its name, has its user, only one, and may be active or not. We have to decommission shopping carts after some time. That's very interesting. But first, we need to remember queries. What customers are going to do with this data? First, we need to be able to query user's active card. Not like working with customer wish list, but working with active card. We need to query all cards for a user to show list of possible, to show old cards. For example, remind something. You still would like to buy this thing? Maybe. Let us earn some money. Let you get good thing. User needs to view products in their cart, obvious. User needs to add a product to a currently active cart. And user needs to remove product from their active cart if he or she doesn't want to buy it anymore. Totally fine. So we need to understand needs, what some measures we might need to protect ourselves for the future. Old cards in the database may be a potential of attack for some nasty competitors. The story is if this item can be spawned in an unlimited way, bots may try to spawn many products for a single item, or bots can spawn many cards. We can counteract them in a different way. We can have rate limiter on product add service to avoid overflow with items. One very interesting feature of Cassandra is when you record data, this data, like insert something into the database, this record might have time to live. So how soon it will be deleted? By default, data is not being deleted. By default, data is being stored forever. But for example, we decide what if customer didn't access its basket or order for, not order, yeah, but a card, we going to delete this card after 60 days, after 2 months. With Cassandra, it's interesting. We can define default time to live for this table. So any created item will be deleted after 2 months of an activity, for example. So it's happened automatically and we don't have to worry about that anymore. That is an example. Maybe your application should not delete cards after 2 months or should do it after a year. But that's interesting to understand. It's important to understand various possibilities. So based on the queries we decided, we can think about following items: products by cards, all cards by user, and active cards by user. Those going to be different. And going closer to physical data model, we will speak about card products to user cards. Notice again, there are going to be included this way, so we don't, they're shown like a relation on here D diagram, but there is no real relation, but then that's a non-relational database. So then we create table user cards that might look like that. That's by the way, I forgot to tell you, it's Cassandra query language. Cassandra query language is intentionally designed to be similar to SQL, to be like in the subspace of SQL, to be familiar to you, so easier to learn. But there are some possibilities what might look different. For example, when we create table user cards, we are going to set default time to live of 2 months, so we don't have to clean up those manually. Okay. Same idea to our card products. The story is then you add product to a card, it has to be added as it is. So we denormalize, we duplicate this data, because if then shop changes something in this original product, we still will have the same data like it was on the order moment on the customer, and also we will not we will not query multiple tables, we will query only one. So we duplicate product ID, product description, product name, things like that. For the user profile, each user has some personal data like addresses, emails, and cards. So our idea is going to be for a customer profile very simple. Query user data by ID and query user data by email address. So idea is going to be simple. We biological data model can think of like we could go with that. User having user ID as a primary key, user email, first name, last name, like addresses, and so on. That sounds familiar so far, but there is a little adventure. It will not work like that. And now you must be surprised. Like, what do you mean it will not work like that? We have user ID, we have user email, we can query data. Like, why would we need two tables? But the story is, people, we do need two tables in this case. And now you must be surprised. Let me explain you why. Take a look at our requirements. We need to be able to find user data by user ID. And we need to find user data by email address. In non-distributed data, you could totally go with a table like this. In distributed data, it will not work. You remember, I've shown you how we split table across multiple servers. And I told you what this data is being distributed based on some part of a key, partition key. For example, if here we decide what user ID will be partition key, as we see here, then all data will be split across multiple servers, all our lists of users based on their user IDs. Basically, we will have millions and millions of small partitions, single row partition, because each user ID is unique. There are no two different users sharing the same user ID. It's always going to be unique. We are going to have millions of small partitions. And here the problem comes. If you know user ID, then Cassandra will go and reach a particular server knowing this user ID because how the data is distributed across multiple servers, it's known. But if you are going to find a user using its email, because ID was used as a partition key, not email or something else, you cannot do it anymore. Why? Because ID is partition key, so ID defines distribution. Email does not. And can you retrieve your data having this table like that when you have email? You know what user is somewhere on one of the servers. If you have one single server with all the users' emails there, it will be one single query, and you ask this server, that's my email, I want to have this customer. Boom, done. But the problem is, when you have millions, hundreds, millions, billions of customers, like how many billions of users now on Facebook, let's say, that doesn't fit a single server. You have to partition your data across multiple servers. And then, if you don't know partition key of how the data was stored, you will have to go and ask each and every server of your cluster. And there might be 1,000 of servers. It's not going to be fast. So complication of a partitioning, really, you need to understand partition key. Now, that's why we speak about like real data model we will be using is user and user by email. If you know user ID, you can just go get this user easily. But if you know only email, then you will need to get user ID by email first. So we have dedicated table user by email. User's data is duplicated into different tables. You have user mail stored in both, but in the second table is used as a partition key. Very interesting thing. And that's how it works in the end. That means you will need to do 2 read queries. And that's perfectly fine because reads are very, very fast with Cassandra. Okay. So in the end, we have this user table. We should not forget what password hashing is very important for us. So password never stored in plain text. That's a reminder mostly for students, if there are any with us. I don't want to stick to hashing here because, well, we have more other things to discuss today. So let us keep moving. User addresses will be stored as user-defined type. That is very importantly a point. List of frozen addresses. I will not explain frozen part right now. Just believe me, it will work better for us. But what matters for us the most, in Cassandra, you can define your own data types. So here we define data type address, and then we use it in a table, and each address will have type, street, city, whatever. So it's very convenient to use, and single user can have multiple different types of those addresses. User by email then is our primary index, kind of manual index, we can say, which returns user ID for an email address. And I'm thinking, David, what do you think if we go with the next hands-on part now, actually? Do we need to explain order processing data model first, or we can go straight to hands-on part?
I think we can go straight to the hands-on part.
Okay. Yeah, because I want to work more with a code today, with the application, more than with the data modeling. For data modeling, we have dedicated workshop. Okay, so how it goes? You are ready to proceed?
Sure am. Let's go.
Good. I'm switching to you. Yep, here we go. And I love this t-shirt. I totally need to have one like this.
Yeah, I wish it were a real t-shirt. It's made in Photoshop, but it's such an important idea and such a foreign idea for those of us who come, and most of us do, from a relational world, that denormalization is the new normal. You also saw, as Alex was going through the data model, that one of the conventions that we'll use is we'll name tables by, like employee by or customer by email, indicating how the data is organized or how the partitions are defined in a given table. So denormalization is in fact the norm, and Alex did a great job explaining why that's important. So the next thing we're going to do is we are going to go and create the schemas and populate them. And let me create schemas and populate them. And in order to do that, we're going to jump back into the Astra UI. And you might have to log in if yours has been sitting the whole time. I've gone in and done a few things in mine to keep it active. Just to show you something we didn't look at, here's our databases. And I have the demos database I've selected at the bottom. And it's active. Now I can look at health. Since the database is active, you get requests, write latency, reads, a lot of information available to you. You can set the refresh period. You can set how long, how much data you want to look at. So a lot of useful information about the database, information about connecting to the database. We'll come back here because our backend piece, the Spring Boot portion, will have to connect to the database. So we'll have to go here and do some things. The change data capture, if we want to stream changes to another source, that's here. Settings for the database, a few other specific things like private endpoint. Someone had asked about that. We're in Google Cloud. That's a premium or paid feature. And very importantly, the CQL console. I mentioned the CQL console, and what I said is the CQL console is going to let us run Cassandra query language against this database directly from the browser. So that's where we're headed. And what we're going to do is create the data model that Alex has been talking about. The first thing we're going to do is use the key space. If you remember, we created a key space and it was called e-commerce. So I'm going to copy that. And again, this looks just like our relational database. Actually, instead of copying it, I'm going to type it. And I'll type use and E, and I hit the tab, and there is code completion in CQL, in CQLSH. So it chose the only key space that begins with E. So now you can see my prompt has changed, and I'm in the e-commerce key space. I can also say describe, and oops, I guess I need to type one more character before it understands. So DESC stands for describe, key space. We can say key spaces, and that's a list of all the key spaces that I have. I created the e-commerce key space. The other key spaces are all system key spaces that belong to Cassandra or Astra. So we are in the e-commerce key space, and I can issue a clear command here just to clean up my screen. And here is the CQL to create the various tables that Alex talked about. And you'll notice it looks an awful lot like SQL, and that's deliberate, as Alex said. Here's that category table. And I do want to point something out in the syntax. The category table has a primary key that consists of two fields, parent ID and category ID. When you have the single parentheses here and multiple fields, the first field is the partition key. So all the categories with the same parent ID will be in the same partition. And partitions are guaranteed to be stored in the same physical server or node. And then within a parent ID, the individual rows are ordered by category ID. So the rule is data is distributed or grouped by partition key and ordered within the partition by clustering key or clustering column, and we use both phrases. I'm trying to see if we have a more complex one. Yeah, we do have one here. The primary key has 3 parts: card ID, product timestamp, and product ID. Card ID is the partition key, and then cart products are ordered within the cart by timestamp first, then product ID. So we're going to go ahead and create these tables. And I'm going to do that the quick and dirty way. I'm going to copy the CQL using the copy command there and paste it. And now the tables are created. The next thing we're going to do is we're going to enter a bunch of data. Fortunately, you don't have to do this manually. There's already data predefined. I do want to point out something about the, we'll go back to that category table. Notice the data type of parent ID and category ID. The data type is a UID, a universally unique identifier. And you might be asking the question, why do we go and use this lengthy, complex UID thing where a simple, if this were a relational table, my parent ID would probably start with 1001 or something like that and just be a sequence of numbers. The reason we don't is because of the distributed nature of Cassandra. Because we are in a peer-to-peer architecture, you may be doing inserts on Cassandra instances in 4 different data centers on 4 different continents. And maintaining a single sequence table between all of those would be super time consuming and super complex. So instead of that, we're going to generate UIDs, which are essentially random unique identifiers, instead of our relational model where we typically use sequence numbers as identifiers. So that's a difference that you may have noticed. So here are all of the inserts. Again, the inserts look like SQL inserts, so I'm going to copy those and execute them in the CQL shell. So we'll paste them. I'm thankful I didn't have to type any of that. And we'll go ahead and follow what our GitHub repo says. It says, well, let's do a select star from category. Now, as Alex said, the select star from category is a very expensive or potentially very expensive query because we're talking about every row and the rows are distributed. As I said, we could have a massive cluster broken down into 4 data centers stored across different geos. This isn't the query I normally want to do, but for way of example here.
Right.
Yeah. Right. This requires a full table scan. On the other hand, if you really need all the data, there isn't a faster way to do it than a full table scan. But part of the data modeling is going to be to effectively partition, that is group, and use clustering keys to order our data to support the queries that we actually use. So this isn't a query I'd really use. I'm just doing it as a quick and dirty test. Another thing you can do says the top categories of the product hierarchy can be retrieved by using a parent ID, and it gives the parent this ID, the UID. So let's try that. Select star from category where parent underscore ID is equal to this. Now, what this is going to do, this query specifies the parent ID in the category table. And the parent ID for the category table, I'll go back to the table definition up here. The parent ID is the partition key. So what this is going to do is find all the rows associated with this parent ID, and they'll differ in the by category ID. So we come back, and here are those rows, and so clothing, wall decor, tech accessories, cups and mugs, and what I might do for this query is something like this. I might say select name, and now I get clothing, wall decor, tech accessories, cups, and mugs. So that table was organized. The data is organized by parent ID in order to support queries by parent ID. So we've populated the data. And Alex, I'm going to do the next couple of things here, kind of munch them together.
Yeah, I wanted to ask you.
Yeah. So in our architecture, we defined data in Astra. We defined a backend, which is Spring Boot. We talked about streaming sort of as a side from that. We talked about the front end, which is React, and the client, which is using a browser, mobile browser, desktop browser, doesn't matter. What we're doing here is interacting directly with the database. The client is the database console here, but in reality, we want the client to be our Spring Boot backend. So in order to support that, we're going to have to allow Spring Boot to access Astra. So step 5 is to create some tokens. So we're going to I'm going to go back and click the database tab, and I'm going to create a token. In order to do that, I'm going to go to my database, which is demos. And as I mentioned before, the user interface has changed a little bit. So I'm not going to go to organization and token management. I'm going to go to connect, and I'm going to say generate token. And let's see, I actually want to generate a different kind of token because I want the token to have, let's see, I can't read my small screen. I'm going to generate a new token. And now I can specify the role for the token. So the token is going to represent connections or users. And I want this user to have, I think it was database administrator and that's fine. Database administrator has all of these permissions. I may have just violated the rule of least privilege and granted more than I need, but for the demo purposes, rather than granting less and having to redo it. Yep. In reality, you would very carefully select the permissions that you wish to apply to a token. So I'm going to generate a token. And here's the token, as the note says, copy this or something, because this is the only time you're going to have access to this token. And what I'm doing is I have a Node app on my other screen. I'm just going to copy it to that because I need it. So client ID, client secret, and I'm just copying these because I'm going to need them later. Okay. So we've gotten the token, and I've saved it locally. Next, we're going to need to connect our middleware or backend piece to the streaming, because the Spring Boot is going to code is going to have to connect to Astra, and it's going to have to connect to Astra Streaming or Pulsar. So I'm going to need to do a similar thing here. Select streaming, select the tenant, and if I go down here, I have the tenant details. And now what I need are the tenant name, which is e-commerce dchung. I need the broker service URL, which is Pulsar plus SSL and this stuff. So I'm going to copy that. And I'm just putting this into my note-taking app because I will need to trace it, paste it later. And I don't remember if I need the streaming token. I think I do. So let me copy that anyway. Oh no, sorry, I don't. There's a token manager. And you see I have information about the token that's created. So I'm going to need this information in order to let the Spring Boot code connect to Astra Streaming and Astra DB. So I think I have all of the pieces now. And the next thing I'm going to do is really cool. If you haven't worked with this, it's pretty awesome. We're going to work in an IDE. And as Alex said, we're going to use a cloud-based version of Visual Studio Code called Gitpod. Gitpod works is tightly meshed with GitHub. We're working from GitHub. Notice I've been looking at just the markdown of the README page here, but this is a real GitHub repo, and there's real code here. There's the order processor, the data pieces, the backend piece. The backend piece, of course, is Spring Boot Java. The UI, which is React TypeScript and some JavaScript. There are things like Docker files. All the stuff that you would really use in application is here, and Gitpod is going to give us access to it in an online development environment. Very, very cool. So let me scroll down and find the Gitpod link. I'm going to open this in a different browser. So I'll copy the link address, and that way I can move back and forth between them. And I'm going to create a new workspace. And it'll take a minute to fire up a workspace in the cloud, but it'll be a very familiar VS Code if you're familiar with it, or if not, it is an IDE. It'll be a very familiar user interface. And you can go through and look at all of the pieces of Gitpod when it comes up. Again, if you're familiar with VS Code, it will look very familiar. And we'll give it a minute to come up, but it has the ability to view files, a list of files, the ability to open a file and edit the file. One of the things that we'll be using is the ability to create a terminal that opens up to the base directory of the environment where your application is in the cloud, and we'll use that feature. That is assuming this container starts up. Sometimes it takes a minute or two to get it going. And what we're going to do once that comes up, I may even start another instance. See if that comes up any faster. Looks like this one is coming up. Good. Okay. So this is our very familiar looking VS Code environment. And you'll see that it's going through some opening, creating stuff. But here on the right, you see that we have a terminal window. And if you look in this terminal and in this environment, we have Maven. We have Java. npm. We even have node. Even Docker. So we have a fully loaded, if you will, development environment that we can work in.
Yep.
So the next thing
David,
we're going to do,
David,
yeah,
sorry. I see Catapult extension started on your Gitpod node, but we don't need Catapult for this workshop, right?
right. I'm not
Yeah,
sure
yeah.
how it got started.
It's fine. You can just close data stack screening routes part on the left, like this tab, and use it as a normal IDE. And you can switch off, or easier way actually is to press Command Shift P, go to the installed extensions list, Command Shift P. Yep, extensions. Just type extensions or install it. Yes, I don't remember. Typo. Extend. Yeah.
Show enabled.
Yes. Yeah, go for it. And yeah, disable Catapult. For our students, it will not happen because they don't have Catapult installed. Now you have to reload the browser page. Just update, reload the page.
Yep.
Yep, right. And you will have it running normally with no Catapult auto-launched.
Thank you, Alex.
Yep.
Yeah, and just a note for you who are watching, Catapult is something we use for online exercises. I've been working on some of the background, and so my environment got a little munged up there. So
Yeah.
sorry about that. Thanks for rescuing me, Alex. Yeah, excellent.
Well,
This is
well,
what
well.
you should see.
Yeah, originally I developed Catapult, so I know like perfectly how to disable it, enable it, and so on.
Yeah. So here's the README that we've been looking at, and the next thing we're going to do, I'm going to look at it off to the side just because I'm already there, is we're going to take a look at this environment sample file. And first we're going to copy it to a file called .env. And I'm going to paste, and then I should get there. I need to allow pasting into this environment. So I'm going to do that once. And let's take a look at, there you see the .env file I just created. The next thing we're going to do is we're going to open it in Gitpod. Now I'm going to do that for the command line. gpopen.env. And here's the file. The purpose of this file is to allow us to set all of the token information into the environment, and the Spring Boot application will read this from the environment and use it with the Cassandra driver to connect both to Astra database and to Astra streaming. So that's why I copied down the values here. So I'm going to go and first get my database ID and region. So I'll go back to Astra, go to database. Here's my database ID. Again, it's a UID. I'm going to copy that. My region is US Central 1.
Actually, I have to say what now it's heavily simplified with work what Cedric done. We have to
Yes.
update this because now it's just one console command to get it all.
Yep. And let's see, Astra DB app token. Here's my token. The token begins with Astra CS. So I'm going to copy that. And then the streaming stuff. Oh, and the key space was e-commerce. The streaming tenant. Remember, that had to be a globally unique name. So e-commerce SD Chung. and the streaming URL. And I need the streaming token, which I did not get. So I'm going to go back, go to streaming, connect, select my tenant, go down to token manager, say create token. I'll create a 7-day token, copy it, and there it is. So I have the information. I know later on we're going to hook this up, and maybe we won't get to that, but the next step would be to hook it up so it runs using single sign-on from Google. So I'm just going to put in some dummy values here, and I'm going to save the file, and that file is saved. The next step is to use this file. Let's see. Got database ID, we've got all filled in the details, and I'm going to source the file. What that's going to do is create these environment variables. So source.env, and I can look at them. I can use grep env and note that's env for the environment, not the file. Grep Astra. And you'd think I could type, Alex. And there you go. So these values are stored in the environment, and the Spring Boot application will take advantage of them in order to access the database and access Astra streaming. Then step 7 is enabling social login, which has us go to Google and enable the Google single sign-on. We're not going to do that here using OAuth just because it takes a while. What we are going to do is run some unit tests. This application uses Spring Boot. And if I go in the back end, it's a full application. Here's source, main, Java, service. And we've been looking at category. We have the category entity. And it maps the category entity object to the category table, defines the primary key, the various fields, name, image, products, accessors, setters, and getters. The primary key is defined here, and the primary key consists of 2 columns. In this case, the partition key, which is the first column, and the clustering column. So grouped by partition key, which is part of the primary key, ordered by clustering column, or sometimes called clustering key. The Spring Boot, we're using Spring data here. So there is what we end up doing is we create this category repository. It's an interface, and it defines the queries that we're going to be able to run. The first query is find by parent ID. And what do you think find by parent ID should return? Well, parent ID is a partition key. It's not the whole primary key. So this is going to return multiple entities, multiple rows if they exist, all the rows that belong to a particular parent category. And this one, we're going to return a single row if it exists, because we specified the entire primary key, both the parent ID and the category ID. And I know so many things are strange here, but it is still true that a primary key uniquely identifies a row. just like in relational world. So that's the Spring Boot stuff. There's also a REST controller that allows the Spring Boot data to be exposed over REST. And here's, if we search for categories, following our RESTful conventions, that should return all the categories. And I'm not going to go into detail about how the Spring Boot works here, but to show you that stuff is in there. So let's go ahead and we're going to run a test. There is test code along with this. So I'm going to clear my terminal here. And I'm going to copy the test command, the Maven test command. And I'm in the wrong directory. Oh, I need to be in the backend directory because that's where the Java code is. And as a Java guy, I want to be where the Java code is. So let's
David,
run the test
sorry,
command. Yeah.
there is a question, but we can answer it. You can answer it in a moment. Then this part will be done. It can wait, I guess.
Okay. So we're running. And we've run our 2 tests. And you'll see we got back what the test did is they returned what we returned before. We returned this data directly in the Astra UI using CQLSH. So we went, I don't have that screen open, but we went directly to Astra. This is testing the Spring Boot backend code and seeing that it can access the same data through Astra. And it did it by using these environment variables, and using a Cassandra driver to connect remotely to Astra. So pretty cool. There's a lot of stuff doing there. Yeah, Dominic, I see you did the Google login example. Yeah, it is very cool because then you can just log in as Google. We won't be able to demo creating a shopping cart because we can't log in. But the Google login example is definitely cool. So we got the output we expected. There's another test we can run. Spring Data is designed to simplify accessing data in Spring. And for relational databases, it comes with an OR, an object relational mapper, or is an object relational mapper. In this case, it's an object to non-relational mapper, if you will, but it allows us to deal with data as Java types. Well, in the back end, they are tabular types, non-relational tabular types. And the Spring REST controller allows clients to invoke our Spring backend, and they get JSON objects. So in the backend database, you have NoSQL tables in Cassandra. In the Spring Boot backend, you have Java objects, and they get translated into JSON and sent over HTTP to our React front end or React UI. So there's a lot going on here, and there's a lot of Spring magic, if you will, that happens. A couple other tests. Oops. And I do this every time. I pasted the test up above on the wrong window. So I'll run another Maven test. And I see Aaron is answering stuff online. Thank you. I'm kind of watching the screen and not watching the chat as much as I could while I'm keeping up with this. So appreciate it. There you get back the results and IDs as to be expected. And there's some other tests we can do, but let's take a look at starting the application. So in order to do that, I'm going to change to the e-commerce app. So it's one level back. And I guess I could have copied the whole thing. We'll install the app. And while it's doing that, I'm going to open another shell and instruct Gitpod to open a URL.
You can do it with you can do it via user interface, but you know what? Old school people like me and you prefer console commands, right?
That's right. Let's see, port not found. Not quite ready yet.
It looks like it wasn't executed. You might want to run this command again. Or was it? No, looks like.
Oh, right. I haven't. Thank you, Aaron. I haven't started the app.
Oh,
I installed the last command I gave was to install and build, but I need to start it.
you notice that then I said what together with Aaron and David, our experience makes almost 100 of years. But Aaron started to contradict. Aaron, don't contradict me. I know you work overtime. So that makes your experience close to 50 years. And
right.
that's
Alex
exactly.
and I have 50 years between us.
Yeah.
Aaron's 50 years by himself. There we go. Now the application is actually starting up. The last thing I did was install it, but I hadn't actually started it. And now here's the application. And I can choose an item. There's the hoodie. And I'm going to choose extra large and add it to my cart. And again, I'm not logged in, but you get an idea of how that works and how all the pieces go together. We talked about data modeling, which is crucial to this. And the things I just did way too quickly hands-on were how do we get the Spring Boot application to connect to Astra database and Astra streaming. If you go through and follow the contents of the GitHub repository, you'll also see there's a couple things you can do to see how the streaming pieces work as well. Remember, we said that has to do with some of the asynchronous, but very important, parts of order handling, like pulling an item off a rack, actually shipping it out, and those sorts of things that may be done by humans even, or robots, but happen asynchronously, and our streaming lets us do that. So I think that's as far as we're going to go into the hands-on. We've kind of are running out of time here. So in just a sec, Alex, I'm going to hand this back to you.
Yep. Actually, my part here is almost done because next part is going to be about external service integration. So AUF with GitHub or Google with Spring Security. So I believe we can proceed directly to hands-on 4. What do you think? Because I have basically just one slide left.
Actually, I think we're done, Alex. Since we're over time.
Yeah.
We'll leave hands-on 4 would have been the Google integration, and we'll leave that one as they say in academia, as an exercise to the reader.
Mm-hmm.
We are available in Discord. If you run into any issues, that 100 years of experience, Alex and Aaron and I, and others from our team are happy to jump in and help you asynchronously on Discord after we're done here.
Yep. So then let me publish one more last time materials link. It's going to be GitHub. I'm Nilay, I'm just sending the link here, or better to say, I'm asking bot to insert the link. Those basically the whole hands-on instructions, source code, and so on and so forth. Everything what you've seen right now. Yeah, Nightbot just pasted the link. So there is all. Then let me switch to my screen. You're perfectly right. In this case, yes, because we are indeed a little bit over time. So, boom. Yeah, right.
You know, Alex, I think it's that 50 years of experience. You and I always go over time.
Yeah, we just love to chat too much, like. But okay, those all are interesting topics and some stories with dozens and dozens of joins and applications hanging over. Yeah, good. So, what comes next? First, Discord. To communicate with us, then the workshop is done. You will need this link. Hey, thank you, Nilay. Yeah, I
Thank
believe
you.
we are pretty cool, especially Aaron. Aaron, you owe me a beer now. That's how you make free beer, right? So, Discord. Discord. Here is the link to our Discord server. Good. Now, next thing. Thank you, Dominic. Yep. A very important thing. DataStax sponsors your education and certification for NoSQL, especially for Apache Cassandra. So, you can get proper trainings on the Academy, datastax.academy, or again, Academy command for bot. Academy, correct. In order to get voucher for free, courses are open and free. In order to get a free voucher for the certification, normal price around 150 United States dollars, I believe, you will have to complete courses DS201 and DS220. So one for Cassandra Foundations and one for data modeling. So then you complete those, you write an email to academy@datastacks.com, you get your voucher, you take your examination, and if you paid enough attention during your classes, you're becoming certified Apache Cassandra developer or administrator, which is definitely a good boost to your career. With that said, I think we are done for today.
Yeah, one last thing, Dominic, you asked if saying Bang Academy gets you the link or Bang Discord. When you do that, Nightbot provides the link. So the link is provided by the chat member called Nightbot. It's done sort of automatically.
Good. And don't forget to connect with us on LinkedIn using the links which is just pasted for me and will be pasted in a moment. Yeah, done for David.
Yep.
Last things last. In 2 weeks, DataStax workshops. In just 2 weeks, on 17th of May, we do running Spring applications with Spring Data, being focused on exactly the Spring Data part. So if you are into this kind of things, it may be of a pretty good use to you. Some things we will have to repeat, like about the working with Astra and Cassandra. So you could fast forward that. But for the Spring Boot and Spring Data part, this one is going to be pretty interesting. So I do hope to see you in a couple of weeks. Good. Thank you, Luis Miguel. Thank you, Hayden. Thank you, Dominic. Thank you, Nilay. And thank you, everyone.
Yes, thank you.
Most important thing you have in your life is your time in it, and it's very important to allocate it properly. So what you did right now is you invested your time in your education, and that means you people are great, you are curious, you want to do your job better. We love you, and thank you for spending this time with us. That was Alex and David, DataStax developers. Hope to see you again later. And don't forget to click like and subscribe. With that,
Thank you, everybody.
thank you everybody. See you soon.